Hello, my name is Martin Hahner and I'm a PhD student at the Computer Vision Lab of ETH Zurich. In this talk, I'm going to present our work called LiDAR Snowfall Simulation for Robust 3D Object Detection. In the last couple of years, we have seen many demos like the ones you see here. Yet, they all have one thing in common. They typically only operate well in clear weather conditions. The goal of our work is to extend the operational design domain for autonomous vehicles to adverse snowfall, as you can see here. Here we see two recordings side by side. On the left hand side is a recording in clear weather. On the right hand side, a recording in snowfall. As we can see on the bottom right, the problem with snowfall is that the snowflakes produce unwanted noise in the LiDAR point cloud. The collection and annotation of snowfall data is time consuming and hard. That's why in our paper we introduce a snowfall simulation pipeline that can convert a clear weather point cloud into the same point cloud as if it was captured in real snowfall. Note that valid points disappear due to backscatter introduced by the simulated snowflakes. Our snowfall simulation pipeline works as follows. First, we sample snowflakes on a disk in 2D. And we do this not only once, but for every channel of the LiDAR sensor. Then we stack up those disks and discard the snowflakes sampled outside of the camera field of view. Finally, for every channel of the LiDAR, we take one such slice and check for every transmitted ray if and how much it interferes with the previously sampled snowflakes. If we look at one individual ray, it is possible that multiple snowflakes are interfering with the ray, as we can see in the illustration on the top. On the bottom, we see the received power over time/distance. In this particular example, the orange snowflake would cause the strongest return and overshadow the measurement of the hard target in black. Hence, in the augmented point cloud, we need to replace the measurement of the hard target with the measurement of the orange snowflake. Since in snowfall the road is often wet, we also implemented a wet ground simulation. However, due to time constraints of this talk, it is not discussed further here. On the bottom, we see the results of our snowfall simulation augmenting the clear weather scene on the left. On the top, we see the snowfall simulation of Lisa. We can see that our pipeline mimics a real LiDAR recording in snowfall on the right much better. Here we see some qualitative 3D object detection results of the point voxel RCNN architecture. From left to right, we see the camera reference frame, the network only trained on clear weather data, the point clouds pre-processed at test time with the D-RAW filter, the point clouds augmented at training time with the snowfall simulation in Lisa, and in the last column the point clouds augmented at training time with our own wet ground and snowfall simulation. Ground truth annotations are depicted in color, predictions by the network in black. In the first example, we are the only method that is able to detect the pedestrian in the snowfall clutter right in front of the ego vehicle. In the second example, we are the only method not predicting any false positives. In the third example, we are the only method detecting the lead vehicle that is swirling up snow dust, causing clutter that D-RAR cannot successfully remove. In summary, we achieve more true positives and less false positives than any of the competing approaches. Here we see the quantitative results of the top 3 architectures used in our experiments. From left to right, we report results on 3 different test sets. 1,404 frames collected in heavy snowfall, 2,512 frames collected in light snowfall, and 1,812 frames in clear weather. The first row always shows the results of the network trained only on clear weather data. Then we report the results of 3 competing approaches and 3 variants of our own pipeline. We can see that typically either our snowfall simulation or our snowfall plus wet ground simulation leads to state-of-the-art results in snowfall without sacrificing performance in clear weather. In our paper, we report consistent results for 4 more architectures. If you like our work, please check out our repository where we published our code, and you can find the links to our paper and supplementary materials. Thank you for listening.